In this short video, we'll look at how to calculate crack widths in reinforced concrete structures. This is one of several videos on the control of cracking for reinforced concrete structures that come from the book Structural Design from First Principles. This worked example is based on a case study taken from a shopping mall that was built not too far away from where I live. And the shopping mall had to be closed shortly after opening because of solar induced movements. So we've got some precast concrete units that are going to heat up, and the top part of the section is going to expand. There's going to be a reduced amount of expansion on the underside because there's a temperature gradient. And that temperature gradient is going to set up a strain gradient that is not dissimilar to the strain gradient you would get in a beam subjected to bending moments. And so that's how we're going to analyze this. So the roof of a shopping mall car park comprises 450mm deep precast concrete floor slabs, which spans 16 meters between supports. A temperature gradient of 30 degrees Celsius is induced between the top and bottom of the slab due to solar gain. 1. Estimate the dishing deflection and support movements. 2. Describe the problems that would likely occur if the precast concrete units were not supported using appropriate bearings. The total change in temperature between the top and the bottom of the slab is 30 degrees Celsius, although the temperature difference between the top and the centre of the slab is only half of this, at 15 degrees Celsius. So we can work out what strain is induced due to this 15 degrees Celsius temperature change. That's 12 microstrains times 15, which is 180 microstrain. The famous engineer's beam equation tells us that M over I is equal to sigma over Y is equal to E over R. Since E is equal to the stress sigma divided by the strain epsilon, the curvature is equal to E over Y, epsilon over Y. So inputting the strain that we got from the solar gain and divided through by half the depth of the section, which is Y, we can work out that this temperature change or temperature gradient will induce a curvature of 0.1 times 10 to the minus 6. This curvature will be induced along the full length of the beam and will produce a strain distribution the same as the beam subjected to equal and opposite end moments, as illustrated in 10.13a. In this case, the standard tables of formula tell us that the end slope and midspan deflection are theta is equal to ml over 2ei, and the midspan deflection is ml squared over 8ei. We can rearrange the engineer's beam equation to tell us that the curvature is equal to m over ei. So combining these equations, we can work out what the end rotation is, which in this case comes out at 6.4 times 10 to the minus 3 radians, and also the midspan deflection, which is 25.6 millimeters. Now, we also want to really work out how much the ends of the beam are going to pull in due to that end rotation. And so we can work that out by multiplying the end rotation, which is in radians, by the depth of the section. And that gives us an estimated end movement of 3 millimeters. That's that delta that you can see in 10.13b. So that 3 millimeters of movement would be sufficient to cause cracking of the concrete supports. This problem can be solved with elastic bearings as illustrated in 10.14b, because dishing does not cause stress unless movements are restrained. So This is an important example. A shopping centre actually was closed fairly shortly after opening because of cracking of precast concrete units due to exactly this problem. I hope you enjoyed this short video on the control of cracking in reinforced concrete. There are 6 more videos on this topic available on YouTube and also in the book Structural Design from First Principles. I hope you enjoyed this, and do press like if you found it useful. Thank you.